Okay, this video is on hydrogen bonding and comparing relative strengths of intermolecular forces. All right, so in the last video, we did the first 3 types of intermolecular forces, and I'll briefly go through those after we do hydrogen bonding, and this is the 4th type of intermolecular force. Okay, so as you might guess, hydrogen bonding, you have to have a hydrogen. So the true definition is it's the attraction, or it results from the attraction of a hydrogen atom with an electron pair or a lone pair on another nitrogen, oxygen, or fluorine, and it can only be those 3 atoms. So the question here is why, and that's because if you think about where H is on the table, it's all the way on the left, is a pretty low electronegativity. And N, O, and F are 3 of the most electronegative atoms that we have. So when we have an attraction of an H and a lone pair on an NO or an F, we create this very polar charge distribution. We have a very polar bond. Okay, so then we have a very positive and a very negative partial charge, which results from a huge, which results in a huge attraction. So your most famous substance to hydrogen bonds is water. So here's my Lewis structure, of course, bent. And here's my partial charges. So we've already discussed that water has dipole-dipole forces, okay, partial charge attraction, but water's capable of hydrogen bonding. That's because you have an H attached to an O who can hydrogen bond with the lone pairs, the oxygen's lone pair on a second water molecule. So we already know it's going to align itself with the O here due to your partial charges. Okay, here's that partial negative and partial positive. And so we already have this huge attraction, but then there's also an attraction from this very negative lone pair and this very positive H, which is a hydrogen bond. And the way it's denoted, like it couldn't be more confusing, is with 3 dots. Why they chose 3 dots with a series of electron pairs, I don't know. But that is the way that we denote a hydrogen bond. I'm going to circle mine so you can see it. So there's a hydrogen bond between the O and the H. And then, of course, if another water molecule came in here with its oxygen, there would be a hydrogen bond there. Okay, so hydrogen bond makes this thing have pretty strong intermolecular forces. So if we go through we've learned 4 so far. Let's quickly go through them and talk about which types of intermolecular forces water has. So of course water has dispersion. We learned every molecule has dispersion. So I'm going to keep a little list here. Okay, water has dispersion because it has electrons that can be moved around. Done. Water also has dipole-dipole because water is a polar molecule, which means there's a partial negative and a partial positive attraction. Water also has hydrogen bonding, okay, because it has the hydrogen being attracted to the lone pair on the oxygen. The only one that we haven't talked about is ion dipole. And water can't have ion dipole because we haven't talked about anything ionic being put into water. So it does not have ion dipole. Of the 4 we've talked about, water is a great example who has 3 types of intermolecular forces. So the next thing we need to, never mind. There's a practice question. So I need to amend my definition just a minute for before we go on. I think I left part of my definition out upon looking at it again. So just add this into your definition. Hydrogen bonding results from the attraction of an H atom on an O, N, or an F. That's very important. I left that out. With an electron pair on another N, O, or F. Okay, so we're going to see that in this practice, that because this H is attracted to this O, makes him very partially positive. That's the reason that this H can then hydrogen bond with the lone pair on the oxygen. Okay, if the H isn't on an O, N, or an F, it can't hydrogen bond. So let me say that again. If the H isn't on an O, N, or an F, it can't hydrogen bond. All right, so that being said, there's a practice question right at the end of your paper that asks which of the following substances would hydrogen bonding likely occur. So answer that for me. You may have to draw some Lewis structures. you can pause this video and then resume when you're ready, and I'm just going to go ahead and go right into it. All right, first example is CH4. Of course, CH4 is methane. Okay, it's got a lot of H's, but it doesn't have an O, N, or an F, and so there is no hydrogen bonding in CH4. All right, second one is H2NNH2. I'm trying to give you a hint at the Lewis structure. 2 N's, 2 H's. Kind of like this. I believe it's a single bond or electron count 10, 12, 14, 2, 4, 6, 8, 10, 12, 14. Yeah, so here's your structure. Again, you might be inclined to say hydrogen bonding. And you'd be right. I almost goofed. Because, of course, I have an H on an N in this case, which is one of my 3. I'm going to make this a very partially positive H, which then would be attracted to the lone pair on the nitrogen. So, yes, this one is capable of hydrogen bonding. Oh, gosh. So sorry. Hold on. Okay. CH3F. Okay, so there we go. This is a polar molecule, right here. It does not meet the characteristics to hydrogen bond. You might be inclined to say yes because you have an H and you have an F, but the H has to be connected to the F. That's why I was very careful to amend my definition. So because the C and the H are connected in all 3 circumstances, this is a nonpolar bond. You're not going to get that very huge partial positive that can then be attracted to the F. So this is a no. Okay, although very tricky to get that right. H2S, of course, looks like this. It's a bent structure, polar molecule, but it does not have an N, O, or an F. Well, it does have an H, so this one cannot have hydrogen bonding. So it was only the nitrogen and hydrogen molecule that fit that description. Okay, so if you flip your page or go to the next page or whatnot, there's a printout I included from your textbook. It's okay. It's like a flow chart. It's a little complicated for my liking, but I figured it's worthwhile if you want another resource. But let's do a comparing intermolecular forces. Okay, and their strength. So we'll do a chart like this. Okay, so strength of intermolecular forces. As you probably can guess, the weakest intermolecular force is dispersion. Okay, by a long shot. Remember, just caused by the movement of electrons. After that comes dipole, which are much stronger because of the polar bonds and the attraction of your partial positives and your partial negatives. After that comes hydrogen bonding. And that's normally where the discussion, would end. We do have ion dipole, which are clear off this chart. And again, remember, we're kind of bringing in another discussion into this by introducing an ionic substance in this chapter, because this chapter is so much, talking about covalent things. But if we did have ion dipole, it would be all the way up here. But remember, that's only if we have an ionic substance dissolved in a polar substance, like dissolving salt in water. Okay, so we don't encounter that very often. Basically, these are the 3 types of intermolecular forces. So a minute ago, we were talking about water, right? And the fact that water actually has all 3 of these, okay? But when you hear people discuss water's intermolecular forces, they only, even though it's got all 3, they're only going to talk about this one. And that's because it's the strongest. So while it's important to be able to name all types of intermolecular forces within a molecule, it's also important to be able to pick the strongest type that's there, okay? So if a molecule just had dipole and dispersion, then you're going to hear somebody talking about its dipole forces because that would be its strongest, okay? Again, if we want to bring intramolecular forces into this, they are off the chart. I mean, they are clear up, 3 feet above my dry erase board, because that is talking about atom-atom interactions, and this is talking about molecule interactions. So one more thing before this video is done, and let's talk about how boiling point relates to this, and we'll do water. All right, so here we go. All right, so let me bring in another water molecule. Here's my hydrogen bond. Okay. All right, so if you're going to talk about boiling a substance, we'll talk about water. The question is, what are you actually doing? And if you're going to boil a substance, you are going to break its intermolecular forces. Okay, when particles are in the liquid state, they have a huge attraction for each other. Huge. And they have these intermolecular forces. And in this case, we have hydrogen bonding. If we go to boil that, though, okay, so we were putting a lot of energy in, a lot. Water has a very high boiling point for being such a small molecule. And it's because it has hydrogen bonds. We're going to connect that in just a second. So because there is a hydrogen bond that exists here between the O and the H, if we put enough energy in that we can break that, okay, then we have 2 H2Os floating around, which would now be in the gas form. So when we boil, we're breaking intermolecular forces, okay, which of course requires a lot of energy. You know, you can't boil water unless you put your pot of water on your stove and turn the burner on, okay? But if we go to talk about breaking intra forces, okay, we're talking about huge amounts of energy. Now, it can be done. You might think that it can't. We can't do it physically. So this can be done because, again, remember, if you're going to break an you're going to break the bond between the oxygen and the hydrogen. And don't call that a hydrogen bond. It's not a hydrogen bond. It's a covalent bond. Okay? Which would then leave you, if you broke both of them, it would leave you with H2 and O2. Okay? Well, that process is called electrolysis. And if I've never showed you that, somebody remind me in class. Electrolysis. Okay? And I'll show you a video of the breaking apart of H2O to form H2 and O2 gas. So breaking intermolecular forces is when you boil something. Breaking intramolecular forces, that's a different ballgame. That's a chemical reaction. Okay, so 2 totally different things here. All right, let's do one takeaway point, and then that'll be it for this video. Let's make a connection between boiling point and intermolecular forces. It's very easy. Let's do this. The higher the boiling point, the blank, the intermolecular forces, okay? And I'm sure you can guess that if something has a higher boiling point, much more energy must be put in to break the intermolecular forces, which means that those intermolecular forces are stronger. So a lot of your questions in this chapter will give you 2 compounds and say, here's the differences in their boiling point, rationalize it. Why? And it always is going to be something about the intermolecular forces.